Hi, this is a circle. What is its area? The radius of the circle is r, and you probably know that the area is given by pi r squared. But where does this formula come from? There are different ways of deriving the formula. I will show you one interesting way. Let's start with a circle containing an equilateral triangle. Obviously, the area of the triangle looks nowhere near the same as the area of the circle. What about if we try a square? A bit better, perhaps. A pentagon, hexagon, heptagon, octagon, nonagon, decagon. The overall shape of the polygon is starting to look a bit circular now, doesn't it? 20 sides. It looks very close to a circle shape. What we're going to do is to derive the formula for a circle, pi r squared, by using the idea of area of a polygon in conjunction with the Taylor series expansion. Let's suppose we have a yellow circle that contains an equilateral triangle, which is made up of three smaller triangles of the same area. Very roughly, we can say that the area of the yellow circle is approximately the same as the area of the three triangles. So the area of the equilateral triangle is the sum of the three smaller triangles. And here's some information about it. R is the radius, and each angle of each smaller triangle in radians is 2 pi on 3. In other words, 360 degrees divided by 3, because there are three equally sized angles. Now, to work out the area of one of those smaller triangles, we need to refer to a well-known formula that relates to this triangle here, where we have two sides and an angle between them. And this is the formula. It gives us the area of this triangle, which is a half times the product of A and B times the sine of the angle between them. Now, for our situation, for the blue triangle here, our A and B will be R, the radius, and our angle theta will be 2 pi on 3. So making those substitutions, this is what our formula becomes. A half times R times sine of the angle, and that simplifies to a half R squared sine of the angle. The total area, that means the area of the equilateral triangle, is just three of these smaller triangles. In other words, 3 times what we obtained in the previous line. Now, if we generalize, let's say we had used a square rather than an equilateral triangle, or a pentagon, hexagon, and so on, with n sides, then you will notice that the only thing that would change in our formula for the total area would be this number, 3, 3, because that number represents the number of sides of the shape. So for an n-sided polygon, the total area would be n times a half r squared times the sine of the angle. What we're going to do now is to obtain an expression called a Taylor series expansion for the sine of the angle. Now, in general, sine of an angle as a Taylor series expansion looks something like this. It has powers of theta on the top with odd numbers, 1, 3, 5, 7, And on the bottom, we have the odd numbers, 1, 3, 5, 7, with what looks like exclamation marks after them. And notice that each term alternates minus, plus, minus, plus. Now these exclamation marks are actually referred to as factorial, and they represent something special in mathematics, and this is what it does. 1 factorial means 1. 3 factorial means 3 times 2 times 1, which is 6. 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120, and so on. So if we make those substitutions in our expression above, this is what it looks like. And taking out a factor of theta from the right hand side, we can simplify it. Alright, there it is again. Now, our angle, of course, is 2 pi over n. So if we make that substitution, this is the expression we obtain. Now remember, our total formula for the area is this one. And now we can substitute for sine of the angle what we have above. And it looks like that. Now this can be simplified, this section here, because you can see that the n's will cancel and so will the 2's. And this is what it simplifies to. Now remember that n represents the number of sides of the polygon. What we want is for the polygon to have many sides. In other words, we want to let n, the number of sides of the polygon, to approach infinity. And when we do that, each of these terms becomes very, very small. In fact, each of them approaches 0. So we can replace each term by 0 when we let n approach infinity. And therefore, this expression above becomes total area will approach pi r squared times 1 and each of the other terms, which is 0. And that gives us total area approaching pi r squared. In other words, as we let the polygon take on an infinite number of sides, the total area that it has will be pi r squared, which of course is our formula for the area of a circle. I hope this gives you an interesting aspect of how we can apply Taylor series expansion. I encourage you to research some more about Taylor series and how they are applied in different situations. Until next time, bye-bye.